In example 2, we have a couple wonderful proofs to complete, and these ones are going to be a little longer. Keep in mind, though, that you don't need to use all the statements there, even if they're written out for you. As a matter of fact, we're going to work together to get to the point where you don't have to have these statements written out, 1, 2, 3. You'll do that writing. Well, let's see what we're given here with this one. I'm going to move this up just a touch here. Hopefully you can still see that diagram. I think so. So we're given that triangle OSQ is isosceles with base QO. We're going to write that down here in our given information. OSQ is isosceles with base QO. We're also given that point S bisects QT. Remember, that's in the given information, so we'll write given here. Now what we need to do is we need to somehow prove that ST is congruent to OS. So this line segment is congruent to OS. What I like to do is I like to look through my given information and see what I can logically make as a statement. So triangle OSQ is this one right here, and we're told it's isosceles with base QO. And that means that these two legs of that isosceles triangle must be congruent. So we can logically state here that QS is congruent to OS. Keep in mind that this diagram does not seem to be drawn to scale. That's okay. So what we're just going to do is we're going to go off of our given information, and we're going to make logical, rational conclusions. So the reason for this, that QS is congruent to OS, is that's just the definition of an isosceles triangle. Okay, well, I think we're kind of at a stopping point there. We've got to somehow link OS and ST. We haven't done it yet. All we've stated is OS is congruent to QS. Let's see if the other given information helps us. Point S bisects QT. So here's S, here's QT, and that means QS must be congruent to ST. That's what bisect means. It means cut exactly in half. So we can logically state that QS is congruent to ST. That is just the definition of a bisector. And you want to use that terminology here. You want to use the definition of a bisector. However, we do know that S would also be a midpoint here. We don't use the word midpoint here, so we're going to try to stay away from that there, but I don't think you'd be wrong if you said that. Now, for number 5, let's see if we're allowed to prove that ST is congruent to OS. And you may have to rewrite these a few times to get them just right. And sometimes I do that. Sometimes I reach a stopping point, or I figure out that I maybe should have proved something or a statement down the line a little bit. And that's okay. So just because I have a marker here that's permanent, I need to do it right the first time. But you're going to be erasing a little bit when you try these on for your own or for yourself. So let's see, could we conclude that ST is congruent to OS? Well, let's look here. We've got QS is congruent to OS and QS is congruent to ST. Therefore, if these two pieces are congruent to the same thing, they must also be congruent. You can think about this like 5 is equal to 2 plus 3, and 5 is equal to 1 plus 4. Therefore, 2 plus 3 must be equal to 1 plus 4. Now, that's kind of a simple example, but you're linking statements together in a fashion that is known as the transitive property. So when you're using two statements that have the same piece of information, and you're linking if A then B, if B then C, if A then C, you'll hear that a lot too. That's called the transitive property. That completes this proof. We've proven what we wanted to using our given information and logical statements and reasons. So let's try B right now. Let's see if we can get this one done. In B, we're given that triangle KMO is isosceles with base MO. So let's write that down in our given information. And that's really the only piece of information we're given. With base MO. So all we know about an isosceles triangle is that the legs are congruent. So if this is MO, we can make the logical conclusion that KM is congruent to KO. And that's just the definition of an isosceles triangle. If you look at our proof statement though, we've got something here about angles. We want to prove that LMN, this angle, is congruent to KOM, which is this angle. Well, if we look at these two angles, they're vertical angles. And if we look at these two angles, we'd want to prove that they're congruent, and then we could prove by the transitive property that our proof statement is true as well. So I think right now what I'd like to do is try to get this angle here congruent to this angle here. We're allowed to do that. So this is the angle side theorem. In a triangle, when two sides are congruent, the angles opposite of them are congruent. And so we can say that angle KMO is congruent to KOM. And the reason is the angle side theorem. And if you wanted to write the whole thing out, you could. In a triangle, if you have two congruent sides, then the angles opposite of them are congruent. So this is the angle side theorem. Okay. Now we want to prove here that these two angles are congruent. So we can prove that angle KMO is congruent to angle LMN. Why? Well, they're vertical angles. So we know that vertical angles are congruent. Now it looks like on the diagram that we've actually proven what we were supposed to. We have just one single arc here. You could use your tick marks. You could put one there, and one there. They're all the same angle. Here they're vertical angles, and here we've got the angle side theorem. But we want to prove now that angle LMN is congruent to angle KOM. We can do that actually by the transitive property. We can see here that we have KOM being congruent to KMO, KMO being congruent to angle L, should be an L there, LMN. And therefore, if these two angles are congruent to the same angle, they must also be congruent. So we can logically make our proof statement, and when we're linking these two statements together in that fashion, that is going to be the transitive property for sure. And that's what we're asked to prove.